So welcome back everyone for the second part of the morning session today. So we're delighted to have Professor Jarkko Kari here. I don't think with this audience he needs any particular introduction, but he's a distinguished mathematician and computer scientist from the University of Turkey. And he's going to talk to us today about low complexity coloring of the two-dimensional grid.
Thank you very much, and thank you very much for the invitation and for organizing this wonderful meeting. So in Finland, when you get a doctorate, you get this kind of really nice hat and a sword, and you really have never an opportunity to wear the hat. I don't know where, you cannot use it anywhere. So coming to a conference with this title, Hatfest, I of course have to take a picture and put it here on the slides. to wear the hat even once. All right, so we all know what we have here. We have a tile, single tile that foresees non-periodicity. And in this talk, I mean, we all love aperiodicity, it's a great concept, but in this talk I will kind of look at the complementary property of tiles that allow periodicity or force even periodicity. So of course, if you want to find tiles that are aperiodic, if I tell you some conditions that guarantee that these tiles admit periodicity, then you know that don't look here. I mean, this is not where you are not going. This is where you are not going to find any aperiodic tiles. So maybe it is still relevant to this topic also. And this forcing of periodicity happens, for example, obviously in crystals. And the idea is that if you have a sufficiently low number of local patterns, they force the global structure to be periodic. So like in salt, if this sodium and chloride attach to each other in very limited number of ways, when they come together, you are forced into a periodic structure. And so I look in this phenomenon in the context of a square grid or a rectangular grid, colorings of grids. And I do it in any dimension, not just in the plane. So my objects are colorings of ZD, d-dimensional square grid. Okay, that's also quite simple and quite maybe not what most people in this audience are doing. Grids are boring, many of you, I suppose. But still, for my methods to work, this underlying structure should be a group. And grid ZD is obviously a group, commutative group. So I call this configuration. So configuration is a coloring of an infinite d-dimensional grid using just finite number of colors. And then the global, the local constraints are given in terms of finite patterns that you see in the configuration. So I take some finite shape, let's say D, which is just a finite collection of cells, and I slide it across my configuration, and I record all the patterns that I see of this particular shape. I call this D patterns, if D is the shape. And notice that this shape doesn't need to be connected, or it's just a finite subset of cells. It can be totally disconnected collection of cells. You still slide it around across your configuration, and you record the patterns that you see. So here we have at least these 4 types, and let's assume that there are none more in the, I mean, this is just a finite part of my infinite configuration, but if it continues kind of the same way, let's say that these are the only 4 patterns that you have. And we count how many you have. That's the pattern complexity of the configuration with respect to this shape. So here we have a complexity 4 with respect to this termed upside down T shape. And when does a configuration have low complexity? I define it as follows. I say that a configuration has low complexity if the number of patterns is at most the size of the shape, meaning the number of cells in your shape. Okay, so here this example is a low complexity configuration because we have 4 different patterns and the size of the shape was also 4, so this inequality is satisfied. And this threshold turns out to be a relevant one, meaning if you allow more patterns than the size of the shape, then you kind of cannot expect that it would force the structure to be very rigid or very global structures on that. That would allow you possibly to have infinite entropy in the allowed configurations. But when you are under this bound, the structure is quite restricted, as we will see. And periodicity, we all know what it means. Periodicity just means that some translation keeps your coloring unchanged. So when you shift your coloring by some arrow, all the colors will map to the same color. And the strong periodicity, or here I call it 2 periodic, if we have 2 periodicity, we are in a 2-dimensional grid, so that the configuration is 2 periodic, 2-dimensional configuration is 2 periodic if you have periods in 2 different directions, which then implies that you are periodic in every rational direction. Horizontal and vertical periods also. All right, and there are some very interesting questions in this setup, and I will mention 2. One of them is an open problem, and one of them is a recently closed problem in this setup of low complexity configurations. And the first question is still open. This is Niva's conjecture from 1997. So here we consider 2-dimensional colorings only, and the shape that I'm using is some rectangle. Okay, let's say 6 by 4. And the conjecture by Niva is the following. He claims that if a configuration has low complexity with respect to some rectangle, then this configuration is supposed to be periodic. This conjecture is a kind of very natural generalization of a well-known and not very difficult result for 1-dimensional colorings. This is so-called Morse-Hedlund theorem. So if you have a 1-dimensional infinite sequence of colors, then if for some n you have only, or at most, n different subwords of length n in this infinite work, then the work is known to be periodic. So this is a 1-dimensional Morse-Hedlund theorem, and as you see, the Niva's conjecture is quite a kind of straightforward generalization of this to 2 dimensions. So it's still open, but we know some bound on the number of patterns that is enough to guarantee periodicity. Sur and Kra proved that if the number of patterns is at most half of the size of the rectangle, that is enough to guarantee periodicity for some rectangle. Now you may ask why 2 dimensions, because of course all the concepts can be generalized to higher dimensions. So let's say, what about 3 dimensions? Could we make the same conjecture for 3-dimensional colorings? Well, already I suppose Niva knew that this is not the case. I mean, there are very simple counterexamples that show that this does not extend to 3 dimensions. And here is a simple counterexample. So pick vertical bar, black bar, and a horizontal one, and make them apart from each other by some number, let's say n. So they are not crossing each other, but there's a distance n between. This is not a periodic configuration in 3D, but it is low complexity configuration with respect to a cube. Let's say you take n by n cube, n was the distance of these 2 bars, and let's count. How many patterns, cubic patterns, do you see in this configuration? It's easy. First of all, you have the all-white pattern. Then you have those patterns where the vertical bar pierces through your cube. And you have n square choices where it might pierce through your cube. and then you have n squared choices for the horizontal bar to pierce through the cube. But the cube is not big enough so that both bars could pierce through the cube. So that's the total number of different patterns that you have. And that's less than the volume of your cube, which is n to the power of 3. Right? So it's low complexity, it's not periodic. Okay, so in the second problem associated to low complexity configurations, I will go from patterns now to configuration. So in the previous discussion, I started with the configuration and I extracted patterns out of that configuration. Now I can go the other way around. So let's say somebody gives me a collection of D patterns for a fixed set D, and these are my allowed patterns. And then I take the collection of all configurations, all colorings, where I only see allowed patterns. So it's like an atlas. I think Heim called these atlases. So you have allowed patterns, and you are only allowed to see in your configuration, in your coloring, one of these allowed patterns. And this is the subshift of finite. This is how we define in symbolic dynamics the concept of subshift of finite. This collection of configurations. So for example, let's say I take these 4 patterns as my allowed patterns, so that my original configuration belongs to the subshift or SFT that these patterns define. But then I also have many other configurations. For example, the checkerboard is also in my subshift because the only D patterns that I see here are these first 2 and they are both allowed. Or this one could also be in the subshift. So it's a collection, infinite collection of configurations. Kind of valid timings, let's say. And now we have seen this result by Berger many times, and we can easily state it in the language of the subshifts as follows. We know that there is an aperiodic vampire set, so Berger came up with 20,000 whatever, 20,400 and so on, vampires that I only take in a non-periodic way. So any vampire set you can convert into a set of allowed patterns. There's a very straightforward conversion. They are the same concept basically. Okay? And so what Berger's result means basically, it just means that there's an aperiodic SFT. So you can keep, there exists a finite collection of allowed patterns so that all the colorings that they admit are non-periodic. And they admit some value configurations. And then the main result that he had, maybe the stronger result, let's say, was the undecidability of the domino problem. So he also showed that there is no algorithm, there does not exist an algorithm that would be able to tell for a given SFT if it is empty or not. So you are giving these allowed patterns, finite collection of allowed patterns, and you ask, does there exist a coloring where you only see these allowed patterns? And you cannot make a computer program that would be doing that, giving the correct answer for every instance. So it's undecidable. And I'm interested in the same questions, but in the setup of low complexity SFT. So the number of patterns that you are given, the allowed patterns, is small. At most, the number of cells in your shape. And the same questions, does there exist an aperiodic SFT that would be low complexity? What about the domino problem? Is it decidable or undecidable in this setting when the number of patterns is sufficiently lower than the size of the shape? Okay, then to the other problem that is lies within this framework of low complexity subshifts, namely the periodic tiling problem. And this was indeed recently closed by Rachel Greenfeld and Perez Tau. So this, now we are in any dimension D, and a tile here would be a finite subset of cells. Again, it's a cluster tile, it does not need to be connected. just have a finite number of cells. And then you are tiling the group CD just by translating copies of this single tile. You're not rotating it or anything, just by translations. In other words, the valid tiling, or we call it a co-tiler, is a set of positions C such that the direct sum of C and D is the D. So graphically, let's say my tile would be this upside down key letter. Then this position star would be the, let's say, the positions in your co-tile, elements of your co-tiler, and every cell is covered in a unique way by adding, you reach it by in a unique way from a star by one of the offsets given by this tile, right? So the tiling CD we translate only without gaps or overlaps. So that's your configuration. Now, why is it related to low complexity configurations and low complexity SFTs? Well, it turns out that this co-tiler is automatically a low complexity configuration. You just you observe this configuration with the shape which is the inverted tile minus T. And when you go around and you try what kind of patterns do I see, you notice that in each pattern that you have exactly one occurrence of star. Precisely one occurrence of star in your pattern. That's really the definition of what the tiling means. No matter where you are standing, in a unique way, by following the ln vector in minus E, you reach a star. Same thing as saying that from a star, adding a vector in D, you reach your cell in a unique manner. And so you see, the number of patterns is indeed the same as the size of your shape. So it is a low complexity configuration with respect to the inverted tile. It's actually an interesting thing that is also a low complexity configuration with respect to the original tile, which is not so trivial. It's still not very complicated, but it's a nice exercise to students to show that actually the co-tilers of a tile and the inverted tile are exactly the same set. So if you take a tiling by translate of a single tile and you rotate all the tiles 180 degrees in place, you don't rotate the whole tiling around, you just rotate each tile locally around. It's a valid tiling by the rotated tiles. So this is also low complexity with respect to T, not only minus. Doesn't matter. It's low complexity anyway. All right, and so the periodic tiling problem asks, does there exist an aperiodic tile in the sense that this set of valid co-tilers is non-empty, but it doesn't contain any periodic elements. Okay. In other words, is there a tile T such that the low complexity SFT of valid co-tiler is an aperiodic SFT? And the recent solution, so first of all, in the two-dimensional case, it turns out that there is no aperiodic tile. So Bhattacharya showed in 2016 that in 2 dimensions, for any tile, if it tiles by translates, then it translates. If it tiles by translate, then it also tiles by translates periodically. But then in the recent result by Rachel and Terence Tao, it showed that for some dimension, higher dimension D, there is an aperiodic tile. There is such a low complexity aperiodic SFT defined by the tile. I don't know what the dimension is, probably very big, but we will have a talk by Rachel later today, so I think we will hear much more about this periodic tiling problem. I just wanted to point out that this is an example of a low complexity SFT also. let me tell about the techniques that I'm using. I'm using algebra to study these. So my colors will be just integers. So I will just represent each color by an integer in an arbitrary manner. I call it integral configurations. And then I view my patterns as vectors. So here I have now, let's say I just fix the order in which I read them in my shape. So here I would have 1, 1, 1, 0, and I have 1, 1, 0, 1, and I have 0, 0, 1, 0, and 0, 0, 1. So I have 4 vectors, and they are all 4-dimensional vectors in this example. In general, I have dimension, which is the cardinality of D in my vectors, and the number of vectors that I have is at most that cardinality of D, because it's low complexity. If the cardinality happens to be strictly less, then we know that there exists an orthogonal vector. You have fewer vectors than is the dimension of your space, so you will have a vector which is orthogonal to all your patterns, just by basically linear algebra. Because the patterns span a lower dimensional space than what you have here. And now it turns out that even if you have equality, I want to include this equality here, because, for example, in the periodic timing problem, we always have equality in the number of patterns and the size of the shape. So that's kind of important to have equality here also. But that's not the problem, because even in that case, okay, they might be linearly independent, your vectors, so there is no orthogonal vector to them. But there certainly is always then a vector that has a constant inner product with all your vectors. Not necessarily 0, but some constant value. And that turns out to be enough for us. So in our example here, there happens to be actually an orthogonal one, even though there are 4 of them. They are linearly dependent. So 1, minus 1, 0, 0 is orthogonal to them. Here I have drawn this vector like this. So really, it means that when you take this mask, like a mask of a filter, and you slide it across your configuration and you make a convolution everywhere, you get always 0 value in the end. And in this case, you may already see that, okay, I have here 1 and minus 1. It just tells me that no matter where I look, what I have here minus what I have here is 0. In other words, they are the same value. This being an annihilator already, this being an orthogonal vector already tells you that you have a diagonal period. And this is a kind of where we are heading here. I want to express periodicity in terms of this kind of orthogonal vectors. But then I look at these vectors as polynomials. There's a next step of making things algebraic. So I view now my configuration as a formal power series. And this is purely formal. I'm not doing any calculations. I'm not plugging any values in my variables. But I view this as a power series. I take as many variables as there are dimensions in my space. And now each monomial identifies a cell. So cell ij is identified by monomial x to the power of I, y to the power of j. And then I give this term coefficient, which is the number that I have in that particular set. So that's my representation of a configuration as a power series. It's a Laurent power series. I have the values, the powers of the variables run from minus infinity to plus infinity. But that's fine. So this would be the process, and that would be the power series representing my configuration. And this is a kind of a shorthand for how I write it. So configuration is now a power series, infinite sum, where I go through the whole space, and x to I, just a shorthand for x is like a pair of is a pair of a vector of variables, and I is the position denoted by x to I. Now you may notice that So I'm not, as I said, I'm not going to plug any numbers into the variables. But what I can do formally is still that I can multiply my power series with polynomials. That's fine. There's a formal product of a polynomial and power series. So for example, if I multiply my power series by monomial x to j, what happens is that I'm adding j to all the exponents of my variables, so I'm translating my configuration by vector j. So multiplication with the power of x, so power x to j, is the same as translating the configuration by vector j. So it means that I can express periodicity now. I say that I notice that the configuration is j periodic if translating it by j gives me the original configuration. In other words, if I multiply my power series by x to j minus 1 polynomial, I get 0 power series. Right? Multiplying with this just means that I'm shifting by j and subtracting the original configuration. And if I get 0, it means I was periodic. So this leads to the concept of annihilation. So I say that the polynomial, formal polynomial, f annihilates my configuration C if this formal product is the 0 power series. So annihilation by this kind of difference polynomial is the same as periodicity. And these annihilators of the configuration, they are nice. They form an ideal, polynomial ideal. It's the sum of two annihilators. If you have an annihilating polynomial, another annihilating polynomial, you sum these up. That sum is also an annihilating polynomial, right? Because 0 plus 0 is 0. And if you multiply an annihilating polynomial with any polynomial, you are still an annihilating polynomial because you get 0 times something is 0. So any linear combinations of annihilators are again annihilators. Alright, so why is this relevant to us now? So remember, if I have a low complexity configuration, I have a vector with constant inner product with all patterns in my configuration. And that was just a convolution in each position with this shape, with this pattern, just making the convolution. And the convolution is exactly the same thing as multiplying with a polynomial. I mean, making the inner product in each position with this vector is exactly the same thing as multiplying your configuration with a polynomial whose coefficients are these minus 1, 0, 0. Actually, inverted. The shape should be inverted at that stage. But anyway, it's a convolution. So we see that every low complexity configuration has a non-trivial polynomial that gives you a constant configuration. You get the same value everywhere when you multiply with that polynomial. But then if you just multiply further once more, not only with f, but then you have this constant configuration, then you just shift it once anywhere you like, you get 0. I mean, shift and subtract, you get 0. So we see that you get an annihilating polynomial. So every low complexity configuration has an annihilating polynomial. That was what I wanted to get from here. You have a non-trivial annihilating polynomial for every low complexity configuration. Okay, and then turns out that using some results from multivariate polynomials, namely in particular we use the Hilbert-Smooth and such, you can infer new annihilating polynomials. Remember, any linear combination of annihilating polynomials is again an annihilating polynomial. If you have one of them, it turns out, and this is our main tool, that you have also automatically, you get an annihilator which has a very specific form. It's a product of these difference polynomials, the difference binomials. So if you have a non-trivial annihilator, you also have an annihilator of this particular form, special form. product of some finite product of different polynomials. Okay, I'm not going to prove it, but I just very, very vaguely tell you what happens there in the proof. There's a famous dilation lemma that is used in all the papers on this field. Also Rachel and Terence Tower use this and many other papers. So the dilation lemma is the following. If you have this, in my setup, it's following. If you have an annihilating polynomial, then also some dilations of that polynomial are also annihilators. So not if f is an annihilator, then maybe f squared, f x to 3, x to 4, and so on. They are all annihilators automatically. There's some infinite linear progression of larger and larger inflations of your polynomial or dilations of your polynomial that are automatically also annihilators. This is a well-known fact. And then using this, we notice that if you take any common zero to these dilated polynomials, now I'm plugging values into the polynomial, not in the power series, but in the polynomials. If you take any complex number, which is a common zero to all these dilated polynomials, it turns out that that number is a root of unity, and there's actually only finite number of this kind of difference binomials, such that your zero has to be zero of one of these. These are given by the difference vectors in your shape. There's a finite number. So any common zero to all your dilated polynomials is a zero of such a guy. And then Hilbert-Nussdell and such just tells you that if you take the product of these guys, you know that any common zero to your annihilators is a zero of such a polynomial, which means that this polynomial is in that idea also. It's generated by these dilated functions. Okay, so that was just a sorry about the technicality, but that was a kind of the higher reasoning there. Alright, so we get this very funny looking annihilator. So these are difference operators. And so it says that if you have a low complexity configuration, or if you have a configuration which has an annihilator more generally, you can make it zero by repeating this operation of shift and subtract. Then you do it again, shift and subtract. Shift and subtract. You do it finite number of times, you get zero in the end. Each time you do the shift and subtract, you are multiplying with one of these guys. You get zero in the end. If m here would be 1, that would mean that your configuration was periodic. Because in one single step, shift and subtract, you get zero. So here, this is a kind of a generalized form of periodicity. You don't get that in zero in single step, you have to do multiple repetitions of that operation to get a zero configuration in the end. Okay. So these operations also look a little bit like derivatives or they're difference operators. You can do the inverse, which is the integration, and doing the inverse, the integration, it turns out that the configuration, when it has an annihilator like that, the configuration itself is a sum of periodic configurations. The periodic power series. So you can decompose your configuration into a sum of periodic guys. But these periodic guys might actually be over infinite alphabets. That's a kind of a drawback here. Something you have to take care. So they are not necessarily the finite number of different coefficients. You might have an infinite number of integers in your periodic components. Okay, so let's go back to Nivas' conjecture. Remember, everything I said in the previous theorem, it applies in any dimension. It's not two-dimensional. It works in any dimension. So take your counterexample of Nivas' conjecture. Remember, vertical bar and horizontal bar. Well, we know by our theorem that it has to be a sum of periodic configurations. It is, right? You have vertical bar, that's a periodic configuration. You have the horizontal bar, that's a vertical bar. That's a periodic configuration. your counterexample is a sum of periodic ones. Every low complexity configuration is a sum of periodic graphs. And if you like it rather, the annihilator with the difference polynomials, this guy is annihilated by making a difference in vertical direction. Well, this disappears, and make a difference operator in horizontal direction. Well, the other one disappears. You get 0 in the end. Okay, so maybe I have time to show you how we might use this theorem. It's just an example of how we might apply it. So, in multidimensional symbolic dynamics, there's this quite famous subject of finite type called Ledrappier. It's also known as a 3-dot system. So here you take those configurations that you have two colors, let's say white and black, and you take those configurations where you always have an even number of black cells within such a triangular shape. So this triangle is your shape. No matter where you place in the configuration, you will say even number of black graphs. In other words, 1 plus x plus xy is an annihilator modulo 2. So modulo 2 sum. If you view the blacks as 1s, whites as 0s, no matter where you do this calculation, you get 0 modulo 2. So you have an even number of blacks. So you are annihilated by this polynomial, but modulo 2. So this is Ledrappier subshift. This is a very rich subshift. It contains a lot of different configurations. You have a lot of non-periodic ones. So this is a typical example of a Ledrappier configuration. But then you also have periodic ones, two periodic ones like this one here. Okay. These are also interesting because these are space-time diagrams of a very simple cellular automaton where you just do modulus 2 sum of two values, two neighboring values. And now what I claim is that with our method very easily we can get that any low complexity configuration of Ledrappier is strongly periodic. No matter what your shape is. You take a very random shape, you check how many patterns of that shape you have in the configuration. If that is less than the size of the shape, you know that your configuration is supposed to be too periodic. Okay, let's see. How do we prove that? So let's take a low complexity configuration from Ledrappier and now view it as a 0-1 configuration over integers. Don't take modulo 2. Just view it as a low configuration of 0s and 1s without taking modulo 2. And it's low complexity, so you know it has an annihilator, and in particular we know that it has this particular type of annihilator as an integer configuration. But if this annihilates your configuration as an integer configuration, it also annihilates you modulo 2, because 0 you get when you do the calculations, when you multiply your power series with polynomial, you get zeros everywhere. Well, of course, then modulo 2, you also get zeros everywhere. Like 0 mod 2 is 0. So this is also an annihilator modulo 2. And so we have, our configuration has modulo 2 in a two-element field, let's say. We know that it has these two annihilators. It has the one because it belongs to Ledrappier. It has a triangular shaped annihilator. But it also has this special annihilator that comes from our theorem, product of difference. And now what is nice about these two polynomials is that they don't have any common factors. They don't have any common factors because the second one, it's a product. If you look at its irreducible factors, they are all polynomials whose coefficients are on a single line. So if you take it's a product of difference polynomials. Each difference polynomial is, the coefficients are on a single line. and so all its factors are, all the coefficients are also on that same single line. You cannot kind of plot it up, make it fat. They all have to be on a single line. We call this line polynomials. Polynomials whose coefficients are on a single line on the plane. So all the irreducible factors of delta are line polynomials. But on the other hand, the triangular shape cannot have any line polynomial factors, because as soon as you have a line polynomial factor, your polynomial will have like two parallel sides. When you look at the support of the polynomial, you will get your two parallel sides. And in a triangle, you don't have two parallel sides. So you don't have line polynomial factors. So these two polynomials have no common factors. But when you have two polynomials with two variables without common factors, you can eliminate the variable. There's a well-known results again from the two various polynomials that you can get the resultant of these two polynomials. You can eliminate variable x completely. There's a linear combination of these two polynomials which only contains variable y. Okay, this way, variable y, and it's non-zero. So you have an annihilator. It's a linear combination of the two annihilators. So you have an annihilator which is a line polynomial in a vertical direction, only by coordinates, which implies periodicity. As soon as you have an annihilator on a line, it implies periodicity because it kind of gives you a linear recurrence along the vertical direction, which forces a periodicity then, of course. Okay, so you have this vertical, your configuration has to be vertically periodic. Just because we found a nice annihilator. And you can do the same in the other direction. You can eliminate variable y, and then you put horizontally periodic configuration. So your configuration is to periodic. So that was what I wanted to prove. Just as an example of how we might use this nice special annihilator that you are guaranteed to have. All right. So let's go back to Niva's conjecture for a moment. Now I'm not going to give any proofs, I just state the result that we obtained using this technique. We proved the Niva's conjecture for so-called uniformly recurrent configuration, or maybe you know them as repetitive configurations. So if you have a configuration which has the property that any finite pattern that appears in it appears densely, meaning that there's an n, so that every n by n square contains a copy of your pattern. Then it's uniformly recurrent, it's repetitive. And we proved that if you have a low complexity configuration that is repetitive, that actually has to be periodic. Well, low complexity with respect to rectangle, not arbitrary shape. We don't do that. Well, actually, that's not true for arbitrary shape. Okay? But for this uniformly recurrent. And in fact, not only rectangle, but you can take any kind of convex shape in place of rectangle, and you still have this forced periodicity if you are uniformly recurrent and low complexity. Why this is interesting for low complexity? Why is this interesting for uniformly recurrent configurations? It's interesting because every subshift is known to contain a uniformly recurrent configuration. This is really like a Kirchhoff's theorem about minimal dynamical systems, at least in my language, that's where it comes from. So every dynamical system has the minimal system. And minimal systems are exactly the ones given by uniformly recurrent configurations. Okay, so every subshift contains a uniformly recurrent configuration. So it means that if you take any low complexity configuration with respect to rectangle or any convex shape, you know that in the smallest subshift that contains this, you will have a periodic configuration. Or in other words, this configuration will contain arbitrarily large periodic regions, let's say. not necessarily self-periodic. We hope to prove, I mean, that would be Nivat's conjecture, that the configuration itself is periodic, but at least we know that it will contain arbitrarily large periodic regions. So, and it also means that you don't have aperiodic two-dimensional SFTs of low complexity with respect to a convex shape. Because you know that if you have a SFT, there is always a uniformly recurrent element in there, and so that element has to be periodic. So you have a periodic element always. You don't have aperiodic SFTs. With respect to convex shapes. Okay, so I'm running out of time, so let me finish with the questions that remain. I mean, some questions that remain, there are plenty of them. So the last theorem that I told you about was about convex shapes. So what can we say in 2 dimensions for non-convex shapes, or even disconnected shapes? As there exists a low complexity aperiodic two-dimensional SFT, SFT 2D here, two-dimensional SFT. We know it doesn't exist if your shape that your low complex width is convex, then it's not possible. We know it's not possible by Bhattacharya's result if your SFT is a set of co-tilers for some tile. But then we have all the other cases. I mean, you have low complexity that don't come from tilings, so they are not a co-tiler, set of co-tilers, and which don't come from convex shapes. So is there an aperiodic one there? And of course there's the desirability question there also. And in higher dimensional cases, undesirability of, domino problem I should add there, undesirability of the tiny problem for low complexity SFTs in higher dimensions. And here I think, again, Rachel and Terence have something to say. There are maybe undecidability results here, as I understand. And then, of course, Nivat's conjecture test. Still open. I somehow feel that we are close. We know how a possible counterexample should look like. You have these large periodic regions, but still somehow the final step is involved. Maybe it's big gaps. I don't know. Okay, thank you. Thank you for your attention.
Thanks for a very nice talk. So we started late, so we have time for 1 or 2 questions. Does anyone have one?
Yeah. 2 questions. One is, what do you mean by convex? What do you mean by convex shape?
Okay,
Because the only convex shapes I can think of making out of squares or rectangles.
Right. Okay, that's a good question. So I mean, you take a convex shape in R2, and then you intersect it with a plate.
Okay. And the other thing is, I think you answered this, yes, the conjecture is still open. You don't know what happens if it's not convex. You don't have any.
I don't know. We only know it in the setting of co-tilers of the free side, which is a special case. The general case is still unknown.
Any more questions?
Are there similar results for tilings which are these are all lines by square shapes, and for other shapes are there similar results?
So you like not in the square grid, but in some other underlying group. So in our technique, we need some other commutative group structure underneath. So we need the nice grid there. We are looking with my student at the similar questions for their long sets, which are, well, I think most people here know what their long sets are. So I think we can use some of the techniques also there. We don't have any hard results.
I think it's time to move to the next speaker, so let's thank you.